Namaste and welcome to the lecture on linear algebra through geometry. In the last couple of classes we have been looking at given a set of 3 linearly independent vectors, we want to find out if we can generate orthogonal vectors, and we had this idea of Gram-Schmidt orthonormalization procedure where the entire idea of getting orthogonal vectors from a given set of linearly independent vectors was that you try to take one reference vector and then try to project the second vector onto this reference vector, remove that projection. So, you get 2 vectors which are orthogonal to each other, and then what you do is you take the third vector, and project it onto the first orthogonal vector that you had already got, that reference vector, and second vector which we had just obtained in the previous step where we said you project it onto the first axis and then project this third vector onto that, subtract both the projections, and you end up getting 3 orthogonal vectors. And we also said that if you have let us say the matrix A whose columns are basically the 3 vectors that we had u, v and w, our Gram-Schmidt orthonormalization process basically helps us get orthonormal vectors, and we can express this matrix A as a product of 2 matrices, namely Q and R, where Q is the orthogonal matrix and R is basically an upper triangle matrix, and this is what we had seen in the last class. And we said that okay, we get A is equal to QR, and we also studied the properties of orthogonal matrix, right. We said that orthogonal matrix is nothing but a matrix which has the columns whose columns are all unit vectors and they are orthogonal to each other, and it comes with the property that the inverse of this orthogonal matrix is basically the transpose of the matrix itself. And we also had a couple of questions after this. We said like okay, where we go from here, but then one important thing that we want to look at here is other than generating orthogonal vectors, what else can this be useful for? If you see, we had this let us look at this. So, let us say consider u, v and w, 3 vectors in R3, we will just take in 3D, right, u, v, w vectors in 3D. Now, what we have is the following. We figured out that okay, we can take this, let us say I have the orthonormal vectors, I mean I try to get orthogonal vectors out of this. So, how do I get this? I will choose, let us say let me take a different vector, let us say the vector R1 is equal to, let us say, the vector u, the vector R2 is basically v minus projection of v onto R, projection of v onto R1, and R3 is the third vector that we have, which is nothing but in the direction of R1, and R3 is basically this vector w, subtract the projection of w in the direction of R1, and subtract the projection of w in the direction of R2, project the vector onto the direction of R2 of w, project the vector w onto the direction of R2 and then subtract basically the projection, is that right, basically the dot product which you get. Now, this is fine if we have the vectors u, v and w to be linearly independent vectors. Now, what happens if the vectors u, v, w are linearly dependent? So, the question that we have is what happens if u, v, w are linearly dependent? So, what do we have? Let us look at that. So, suppose let us take this the vector u is as such, the vector u, let us take the vector v to be say some alpha times u, where alpha is some scalar, and let us take the vector w to be beta times u, which means what we are trying to say is the vectors b and vector w are basically scalar multiples of the vector u, right. Now what we want to find out is, we want to find out, can we get orthogonal vectors using u, v and w now, where v is a scalar multiple of u and v is a scalar multiple of, I mean w is a scalar multiple of u. Now intuitively it says like we can't get, because they are all in the same direction as u, and you will not be able to get it, but let us just see if mathematically also this works out, and therefore we will try to infer something out of here, right. Okay, so let us take my r1 vector to be the u vector itself. Let us take r2 vector. R2 vector is basically given by v, the vector v minus projection of the vector v in the direction of r1, so into the vector r1. So let us look at what is that, v minus projection of v in the direction of r1 is basically given by v dot r1 divided by r1 dot r1 in the direction of r1. So what we get? We get v minus v dot r1. V is basically alpha times u, so we have the scalar multiple alpha u, and r1 is already the u vector, so we have alpha u dot u divided by r1 dot r1, which I will write it as u dot u. So let me write this as u dot u, and in the direction of u. Now what we see here is alpha u dot u, you can knock these two guys off. So what we get is v minus alpha u, but alpha u is nothing but the vector v itself, so we are going to get the 0 vector. Now what we see is, when the vectors are scalar multiples, or when the set of vectors are linearly dependent, then your Gram-Schmidt orthonormalization process basically terminates when the vectors are linearly independent. And suppose if the vectors are, vectors are linearly dependent, and if the vectors are linearly independent, then what you need to do is you need to basically project the vectors onto different axes, subtract their projections, and you continue till you get to the last vector, right. So what we are going to say is, in fact we can also verify, one can verify that r3 vector is also equal to 0 vector, right. So what is it that we are going to say? We are going to say that if you want to check whether a set of vectors are linearly dependent or linearly independent, well, in the first place you want to check whether they are linearly dependent, you can actually do Gram-Schmidt orthonormalization process. So when you do Gram-Schmidt orthonormalization process, for a set of dependent vectors you end up hitting the 0 vector. So that is another test for linear dependence of vectors, fine. Now again the question is like, where do we go from here? Recall that if we have linearly independent vectors, we just said that Gram-Schmidt process is going to give us it's going to give a set of orthonormal vectors, and we can represent the matrix A whose columns are linearly independent vectors, and from where we have generated these orthonormal vectors which are going to be the elements of the Q matrix. We are going to have A is equal to QR, right. Now the most interesting thing is, as we noticed before, I want to look at what is A inverse. A inverse is nothing but QR the whole inverse, which is nothing but R inverse Q inverse. But we just saw in the previous class that if you have a matrix which is orthogonal, then the inverse of the matrix is basically the transpose itself. So what I am going to get? I am going to get R inverse Q transpose, right, if the matrix A is invertible. If the matrix A is invertible, then you can write A inverse is equal to R inverse Q transpose, right. So now that brings us to another interesting question. We began with the first few lectures of this course where we looked at solving systems of equations, and we understood that look, if I have a matrix A, a square matrix A which is invertible, and I want to solve a system of equations Ax is equal to B, and suppose the matrix A is invertible, I can write x is equal to A inverse into B. This is something which we saw from our first two modules. So the question is, there I have my A inverse, and we defined A inverse right from the beginning. We have been seeing this A inverse is equal to adjoint of A by determinant of A, adjoint of A divided by determinant of A, and therefore we said okay, the determinant of A must not be 0, therefore the matrix is to be non-singular matrix, and all those things we have studied. Now there is something that interesting comes out, like if you recollect in your module 2 we would have studied the idea of Cramer's rule, right, where in which we looked at we employed Cramer's rule to solve a system of equation, right. Cramer's rule, what does Cramer's rule do? Suppose we have Ax is equal to B, assume that A is a 3 cross 3 matrix, invertible, x we know it is a 3 component vector, and we have B which is basically another 3 component vector. So let us do this. B is also a 3 by 1 matrix. Now how did we get the values of x1, x2, x3? We said that the x1 is basically the determinant of this matrix, where we replace the first column of the matrix A with the right hand side vector B. So we wrote this as B1, B2, B3, then we had the second column of matrix A which is A2, and the third column of the matrix which was A3. This is exactly what we had, and we said that divided by this, the determinant of this matrix, which is the original matrix that we had, A1, A2, A3, right. So let us write this matrix A basically has 3 columns, A1, A2, A3, right. Now what did I do? I basically replaced the first column with the B vector, and then I did B, the determinant of B, the matrix containing B, A2, A3 divided by the determinant of A1, A2 and A3. Similarly I could get my x2 and x3 also the same way. X2 was basically the determinant of this matrix, determinant of, we had this matrix with the first column A1, the second column now gets replaced with B1, B2, B3, and the third column remains as such. We have this divided by determinant of A, and similarly we have x3 to be determinant of this matrix which is A1, A2. Now the last column gets replaced with B1, B2, B3 divided by determinant of A. Now what is interesting in all these things is, all these things that we have seen in terms of x1, x2, x3 through Cramer's rule, we see that the values for x1, x2, x3 are basically obtained as the ratio of two determinants, the ratio of two determinants. And what does that actually tell us? That is interesting, because we already saw that the determinant of a 3 by 3 matrix was the volume of a parallelepiped. Now what do we see essentially? We see that the value of x1 is basically the volume of the parallelepiped, with the first column of A being replaced with the column vector B, divided by the determinant of A, which is equal to the volume of the original parallelepiped that we had. So what is it saying? X2 basically it is basically a scaling factor that you get. What is a scaling factor? That is the value which is going to scale the volume of the actual parallelepiped which was obtained with those 3 columns of a 3 by 3 A matrix, and the scaled version of that is going to be the volume that you get when you replace the corresponding columns with the right hand side B vector. So Cramer's rule, if you see, when you say I am going to do a determinant, the ratio of determinants, it simply means that you are looking at ratio of volumes in 3 by 3, and we already know that if you are going to do it in 2 by 2, that is going to be ratio of areas of parallelogram, right. So, what is the kind of ratio of I mean what is the area that you get of the parallelogram when you replace the first column of the matrix A with the right hand side vector divided by the determinant of this original matrix A, which is basically the area of the parallelogram, right. So, this is another interesting interpretation. So, what we get is xi, suppose I have A x is equal to B and assume A 3 cross 3 and A is invertible, then what do we get? Xi for one I is equal to 1 2 3 is basically determinant of A. I will say this is okay, determinant of, let us say this matrix A1, I will replace, okay, let me write this x1 x2 x3, okay. X1 is basically volume of the parallelepiped, with the what do you call the sides being along I will say sides along the directions of the parallelepiped has sides along these directions B comma A2 comma A3 divided by volume of the parallelepiped which corresponds to the parallelepiped with sides along the columns of A, namely A1 A2 A3, columns of A1 comma A2 comma A3. Now, how does that look like? Let us see that. Say for example, I have this, let us say I have this and assume that this is one side of the I mean this is one of the columns of A, and let us take this to be another column of A, and let us take this to be the third column of A. Now, what we get is basically the following: the parallelepiped is going to look like this, the parallelepiped will look this way, and everywhere I am going to draw this. So, we get this parallelepiped to be formed. This is basically where the purple vector, the green vector and the blue vector that we have. Okay, I should, okay, let me do this. Okay. So, this is this is going to be this one, and this vector is going to be okay, this vector is going to be here, and the purple vectors are basically here. So, this is the original parallelepiped that I have. Now, what I do is I change, this is the parallelepiped with sides along A1 A2 A3. With sides along A1, A2 and A3. So, this will have some volume. Now, what I am going to do is I am going to do something else, in which case I am going to do this. What have I done? I am going to look at, I will retain, suppose we say this purple vector corresponds to the A1 direction, the green vector corresponds to the A3 direction, and let us assume this violet vector corresponds to my A2 direction. Now, what I do, A1 is going to get changed now. So, what I have, A1 is going to get replaced with my B vector. So, it could be somewhere else. My A2 vector will remain the same, which is here, and my A3 vector is also going to remain the same, which is here. So, what is going to happen? I am going to have a different parallelepiped right now. So, it is going to be a different parallelepiped that we are going to get. Let us see that. So, this green is going to remain the same, and this is also going to remain the same, which is here, and so let us look at this is also another one and this is another one. So you see that there is going to be a change in volume the moment you put the vector b as one of the columns of the matrix, there is a change in volume. So what we want to do is we want to look at the change in volume that you have, you want to look at the volume here and you want to look at the volume here. So you say that the ratio of these two volumes is basically what is going to give you by x1, x2 and x3. This is going to be x1. Now the second case you replace that with the second column with b, get the value of x2, then in the third one you replace the third column with b and then compute the determinant and you go to get this. So basically what we see is the unknowns are basically scaling factors for volume that you are going to get, right. Now there is one more interesting topic that is that we just want to look at in terms of the eigenvalues and eigenvectors in 3D. Let us just quickly do that and then we will proceed with the idea of vector spaces and things. Okay, so I want to look at eigenvalues and eigenvectors in 3D. We already had seen in this module itself at an earlier stage where we just looked at some specific matrices or transformations for which we said look, the eigenvalues and eigenvectors are very interesting. We looked at reflection matrix, we also looked at rotation matrix in 3D and we said that rotation matrix in 3D will have at least one real eigenvector, because we found that in case of rotation in 2D we did not have this. In rotation in 3D we could at least fix one of the axis, which is like our the helicopter's fan what we have. So what is it going to be? It is going to be fixed at some height and the rotation is going to happen at that particular I mean in a plane. So the height is fixed, which means that direction is fixed. So we said that we are going to get at least one real eigenvector, right. Now how do we compute? We already know, we knew from the idea of our 2 by 2 case where we said look at the determinant of a minus lambda I and so on. Okay, so let us just do that. Eigenvectors, how do we compute that? So how do we compute? Let us look at a matrix A, let A be any 3 by 3 matrix, real matrix. Now what are we trying to look at? We want to look at Ax is equal to say some lambda x. We already said x is going to be that invariant direction, we said that it is going to be the invariant direction that we are looking for, and there are certain things that happen here. What is that? You are looking for those vectors under the transformation of A which will undergo only scaling, it does not undergo direction change, right. Now if you do this determinant of a minus lambda I x is equal a minus lambda I is equal to 0, which is basically the characteristic polynomial here, we get something interesting. It is a 3 by 3 matrix, therefore this is going to be a cubic polynomial. This is going to be a cubic polynomial and therefore a cubic equation, in fact this is the characteristic equation. So you get a cubic equation, it is a cubic equation, right. So therefore you are going to have 3 roots here. Now what are the possibilities that we can have? The first thing that we are going to say is look, the first possibility is all roots are real and distinct. All roots are real and distinct. If they are real and distinct, then each of these eigenvalues will be associated with a specific eigenvector, right, in which case let us say we have lambda 1, lambda 2, lambda 3 distinct. So what are we going to say? We are going to say that lambda 1 is going to be associated with let us say this vector u, and lambda 2 is going to be associated with this vector v, and lambda 3 is going to be associated with this vector w. Now what does that mean? It simply means au is equal to lambda 1 u, a2 is equal av is equal to lambda 2 v, and a w is equal to lambda 3 w. Now this is the case when we have lambda 1, lambda 2, lambda 3 are real and distinct. Let us consider the second case. Case 2, what I am going to do? I am going to say one of the roots is repeated and all three roots are real. All three roots are real, right. Now assume that we have there is one root lambda 1 and the second the other two roots are basically lambda 2 and lambda 2, right. These are the three roots and they are all real. Now in which case this lambda 2 is basically a repeated root. We had a problem with this repeated root when you looked at eigenvalues and eigenvectors in 2 dimension. We in fact if you recall we looked at this matrix 1 1 0 1 and we said that we are going to have lambda minus 1 the whole square to be the cube characteristic polynomial and equal to 0 is basically the characteristic equation. Lambda is equal to 1 was repeated and we just had only one eigenvector. We did not have two eigenvectors for this matrix I mean because you had despite the roots being the roots are repeated in this case but we just had only one eigenvector associated with it. Now here we have two roots, are we going to face the same problem? The answer to that is no. We may not, but the point is if you have repeated eigenvalues, let us see what happens. If you have repeated eigenvalues there is a chance that you may get we will discuss this in detail when we do eigen subspaces at a later point of time when we do vector spaces and stuff. So what we are going to do is we may get two eigenvectors corresponding to lambda 2. Now how is that possible? We will just conceptually understand and we will proceed further corresponding to lambda 2. Now what is it that we are looking for? We are looking for a minus lambda 2 I times let us say some x is equal to 0. Now this is of the form, this is a homogeneous system of equation, let me put this as say some bx is equal to 0. Now what is interesting is when you have bx is equal to 0 there are three possibilities that arise. What is that? We have already seen that there can be one single vector which can get transformed to the 0 vector, or you can have a set of vectors along a line which can get transformed to the 0 vector. In this case in 3D you can have a set of vectors in a plane which can get the entire plane get transformed to the 0 vector, and the moment you say a plane you are going to have the plane to be defined by two linearly independent vectors, which is what we had seen when we found the volume and stuff, right. So there is a chance we will see this in detail when we do eigenspaces because that is exactly where we look at what is called as algebraic multiplicity and geometric multiplicity and so on. We will define all that at a later stage, but we will understand that when you have repeated roots in for a 3 by 3 transformation or a linear map that you have, you can have sufficient number of eigenvectors, that is the thing. The third case is where case 3 where we have one real eigenvalue, one real root and a pair of complex conjugate roots, a pair of complex conjugate roots. Why do we say this? Whenever you have a cubic equation you will have one real root and the complex numbers, the complex roots appear in a complex conjugate pair. So you are going to have complex conjugate, a pair of complex conjugate roots. In this case what we are going to say is yes, there is going to be only one real eigenvector. Right. Of course, as I said we will revisit all these things when we do eigenspaces, but since we did 2 dimension and in 2D we looked at eigenvalues eigenvectors, we looked at 3D, we looked at eigenvalues eigenvectors for specific transformation, and now we are looking at eigenvalues eigenvectors for any general 3 by 3 matrix that you have, and we said that these are all the possibilities that you can get as far as the roots are concerned, roots of the characteristic equations are concerned, right. So you get all these things, these are the different scenarios that you have. So the question is, having done all these things, where are we going, what is the next logical point that we can look at. So in the last couple of modules or the last few modules, what we have done is we have understood the entire idea of vectors in 2D, transformations that happen in 2D and so on, and we looked at we revisited our system of equations and tried to interpret them in terms of vectors, I mean from the column picture and so on, and we studied a lot about vectors in 2D transformations and all those things. We found that there are certain properties which 2-dimensional things have, and then what we said, okay, having understood 2D clearly, we went on to look at 3 dimension, and in 3D we looked at, okay, we defined how a vector in 3D looks like, we looked at what is cross product, and we looked at the volume of a parallelepiped and so on. We also tried to look at the idea of system of equations, and given a set of vectors we also figured out how to get the orthogonal vectors from it. We actually discussed, because when we looked at cross product we were also looking at the idea of a vector which is orthogonal to a given set of vectors. We were basically looking at the cross product from that perspective, and we defined cross product, and we also looked at Pythagoras theorem from the cross product perspective, and we did all that. So naturally the next step that we want to do is, having understood all these things, the next step that we want to do is we want to go to a general n-dimensional vector space. We may not be able to get visualizations like what we had here, but whatever visualizations and whatever ideas, geometry that we have got equipped with in this journey, it will help us go forward in higher dimensions, and wherever this higher dimension the visualization is not going to work, we will take the help of algebra and we will be able to interpret it in the algebraic terms itself. So from the next module what we are going to do is we are going to look at the idea of general n-dimensional vector spaces and so on. We will look at subspaces, basis, dimension, and a lot of other things. Thank you. Namaste.